This video is 8.7, Standard Heats of Formation. The standard heat of formation is shown as delta H naught sub F, and it is defined as the enthalpy change for forming 1 mole of a substance from its elements under standard conditions. So this is the standard enthalpy to form some compound from its constituent elements in their standard states. Standard heats of formation can be found in Table 8.2 in your textbook, and there is a whole list of them in Appendix B. You won't see any delta H naught sub F standard enthalpies of formation for pure elements, so elements in their atomic state, like carbon, H2 and Cl2, and other diatomic elements, or things like S8. Remember, these are the same types of things that we saw had an oxidation number of 0. And they also, because they're pure elements, have a standard enthalpy of formation equal to 0 as well. And here I have Table 8.2 shown. It's just a table, and for any compound or a chosen few compounds, there are different values of the delta H naught sub F. Now, just be careful when you're working with water, or any compound for that matter, but especially water. The delta H naught sub F is different for water vapor and liquid water, so just be careful when you're looking at water in your reaction to make sure that you're working with the correct one, vapor or liquid. Now these equations to solve for delta H naught sub F, or maybe not to solve for delta H naught sub F, but to find 1 mole of a substance in its standard state from its constituent reactants as elements will look like this. If we want to form carbon dioxide is CO2, and in its standard state it's a gas, and we need to define its standard enthalpy of formation. We will define this reaction as forming just 1 mole of carbon dioxide, and therefore to calculate this we would take carbon in its standard state, which would be a solid carbon, and carbon in its standard state is defined as carbon in the allotrope of graphite. And to that we would add oxygen in its standard state. Oxygen in its standard state is a diatomic element, meaning O2 as a gas. And luckily here, 1 carbon and 2 oxygen will form 1 mole of CO2. However, if we wanted to form carbon monoxide, which would be a gas in its standard state, its reaction for the standard enthalpy of formation, or standard heat of formation, defines that we can only form 1 mole of this compound. And again, we would have solid carbon in the allotrope of graphite. However, oxygen is still a diatomic element, and that's how it would exist in its standard state. But we only need 1 oxygen to form 1 mole of carbon monoxide, and therefore we only need half of an O2 molecule. And so this is a place where you would see 1/2 of O2 written as part of the reaction for the standard heat of formation for carbon monoxide. And for something like water, which would be H2O, we would need 2 hydrogen atoms to form 1 molecule, or 1 mole of H2O, and therefore hydrogen exists as a diatomic gas, so we can keep both of the atoms in that diatomic molecule. But again, oxygen exists as a diatomic gas, and so we only need 1/2 of an O2 molecule to get the 1 oxygen in that 1 molecule of water. And again, 1 molecule, or 1 mole, it means the same idea. 1 mole is just molecules multiplied by Avogadro's number. Again, these are equations that we set up to find the standard enthalpy of formation of these compounds. And so how this was done is in a lab. These reactions were done exactly as written, and then the delta H naught was found for these products, and those are the values that you'll see in the table. How we're going to use them for this class is using this equation. We can use the standard enthalpy of formation of all the reactants and products in a reaction to calculate the enthalpy change of an entire reaction. And to do that, we would say that the enthalpy change of the reaction is equal to the sum of the delta H naught sub F of the products minus the sum of the delta H naught sub F of the reactants. So we're taking products minus reactants. And then what you would need to do is, for every reactant or product, find those compounds in table 8.2 or appendix B in your textbook, or these values would be given to you on the exam, and then plug. Let's use the standard heats of formation or standard enthalpies of formation to solve a problem. Here our problem is, what is the standard enthalpy change for the following reaction? 2NO plus O2 gives us 2NO2. We know that the delta H naught sub reaction, so the standard enthalpy change for the reaction, equals the sum of the delta H naught sub F, the standard enthalpies of formation of the products, minus the sum of the change in standard enthalpies of formation of the reactants. And so what we would need to do is find the values of NO and NO2 from the chart or the textbook. And remember, O2 is in its standard state, so its delta H naught sub F would equal 0. So I found these values. The delta H naught sub F for NO equals 90.25 kilojoules per mole. The delta H naught sub F for O2 is 0 kilojoules per mole because it's in its standard state. And the delta H naught sub F for NO2 from the table is 33.18 kilojoules per mole. Now we need to find the sum of the enthalpies of formation of the products and subtract from that the sum of the enthalpies of formation of the reactants. Now, from the chemical equation, we have to multiply the enthalpies of formation by the coefficient of each reactant and product. And so, for instance, our product is NO2, and what we need to do then to solve for the delta H naught of the reaction is take 2 moles of NO2 from the coefficient here, and then multiply that by the delta H naught sub F of NO2, which is 33.18 kilojoules per mole. That is our one product. And then from that, we subtract our delta H naught sub F of the reactants. We will multiply 2 moles, which is our coefficient in front of NO, by the delta H naught sub F of NO, which is 90.25 kilojoules per mole. And then to that we'll add our 1 mole times 0, which is the delta H naught sub F of O2. So mathematically it does not make a difference. Our delta H naught of the reaction then would be 67.6 kilojoules, because the moles cancel out, minus 180.5 kilojoules, which gives us delta H naught of the reaction equals negative 114.1 kilojoules. This would be our delta H naught of the reaction using the standard enthalpy changes from a chart to solve for that value.